So we talked about the stoichiometry of a chemical reaction, that when you guys balanced them, those coefficients have relative number of moles of everything, okay, balanced equation. And we talked about specifically molarity is the way to describe how concentrated solution is, okay? And this is going to combine molarity, solution concentration, and stoichiometry. So the types of problems we're going to run into, I wish that I could say this is the only type of problem, but basically you're going to be given the volume and molarity of one solution, one liquid, one aqueous solution, and you're supposed to find either the volume given the molarity or the molarity given the volume of another thing. Okay, you see kind of what we got going on. It'll be easier to kind of show you. But like I said, I wish it were always like that, but that's kind of a nice little pattern we're going to start with. So when anybody says the molarity of something, they have given you the concentration in terms of moles of solute per liter of solution. And if you're familiar with one equation, let's see, how's this go? One equation, one unknown. Okay, this one relationship, if we know any two of those, we can find the third thing. So if we know the moles and the volume, we could knock out molarity. Okay, if we know the molarity and the volume, we could get to moles. Okay, if we know the molarity and the moles, we could get to volume. Okay, that's kind of how that works. Comfy couch? Okay, so we're going to count on that. All right, so this is our first solution. This is our first kind of sort of titration. We'll kind of build up to what a titration is. But notice we have two reactants dissolved in water. How do you know that? DAQ, right? Okay, so they go ahead and they give you some information about this reaction between these two aqueous solutions. Now what I usually do, and you're going to see me do it, and then I'm going to kind of pass around the iPad. We should start back with Andrew today. Yeah, yay. But what I usually do is lift these numbers, quite frankly, sometimes numbers just look too blobby. So I put them underneath what they mean something about. So we could even start with the question mark, what volume, okay? So the what volume is associated with the NaOH. So I'm going to find the NaOH, and I'm going to write question mark volume. Okay, what volume of, oh, and then this molarity also goes with the NaOH, so I'll put that under the NaOH, 0.235 molar. Now I know I'm all about being explicit because we're going to have two molarities. We got the NaOH and the H2SO4. But as long as I line it up under the NaOH, I'm cool with that. Is needed to react with, and then they give me volume and molarity of the H2SO4. Excuse me. So I'm going to go up under the H2SO4 and I'm going to write 35.0 milliliters, and I'm going to put 0.108 molar under the H2SO4. So this is one I'm all about working at factor label, carefully making sure things cancel, but I like to break these up into actually 3 steps. I know you can do it all in one step, but you have to be explicit with regard to which solution you're working with. But what I'm going to have you guys do is actually, we're going to start with Andrew, and the first step is to take that volume and molarity of the H2SO4, okay, set up as a factor label, put the volume first, followed by the molarity to get to moles. First step, moles of H2SO4. The second step is once we have moles of H2SO4, we can use stoichiometry to get to the moles of NaOH from stoich. Okay, we have a 2 mole to 1 mole relationship. 2 moles of NaOH are used for every 1 mole of H2SO4. And then actually, literally, I'm going to have a third, and this is how I would do it in my answer key these days. I would have a third step to basically take the moles of NaOH, and then I'm going to use the molarity of NaOH to get to the volume. Use moles from step 3. Sorry, from step 2. And molarity, 0.235, to get to volume. All right, Anne. So I've labeled these slides. So these slides are labeled. So what do you think? I'm totally liking that. Okay. And we'll go ahead and, I've done it both ways. Let's have the next person tap it in. So whatever he sets up, we'll have. Cool. Thanks, sir. Perfect. 3 sig figs. And I like how you wrote moles of what. I think that's great. Any questions about that? Okay. So now the next step, and I think we'll go up here this time. The next step is to link from the moles of the H2SO4 to the moles of the NaOH. And we're going to use, so that's why I have down at the bottom the balanced equation again. So you're going to piggyback on that other moles. So exciting. Like watching paint dry. No, I'm just kidding. It's really exciting because that all looks very good. And we'll pass it over for knocking out the number. Almost do that right. I gotta say, this makes me laugh because you do these things in your head all the time. You're taking 2 times.
Yeah.
00378.
Yeah.
Okay. But 3 sig figs, very good.
Oh, okay. We'll advance to the last part, the coup de grace, okay, is to go ahead now and take a ratio of the moles of NaOH that Ryan found divided by the volume. You know which volume you're going to use? Which volume I'm going to use? Not necessarily. I'm going to start with point.
Oh, wait a minute. No, I told you wrong.
Did you?
Yeah, you're going to use the moles and use the molarity of the NaOH. So the moles Ryan gave over 1 is the way to start.
Okay.
I got my problems fixed up.
That was 7. What was it?
5.6.
7.56. You said over the molarity?
No, just put that over 1 and put units, though, of moles NaOH.
Okay.
And then go back to what we know about NaOH. We were given a molarity. So we're going to use the molarity to get to liters. So what was that?
0.35 moles per 1 liter. That was your hint. Yeah, you got it. Yeah, that's looking really good. Perfect. So Matthew, we're gonna bring it over to you. Ready to knock it out? Do you need to borrow a calculator? Okay. And that should give you liters. Sometimes the kind of annoying thing is problem will say, what's the volume in milliliters? So then you would have that be one. But otherwise, liters are fine. So you guys were pretty good about, you know, if you explicitly write whether it's the H2SO4 or the NaOH, you don't have to break it up into 3 steps. You could just knock it all out in one. Very good. Any questions? Okay. So that's it, you know. There are all sorts of kind of variations on that. Very good. We'll do another one. Different scenario. So let's kind of diagram on the bottom there what we're given in the problem. In this case, we're trying to find the concentration. So question mark molarity of the H2SO4. The volume of the H2SO4 solution is 25.0 milliliters. Okay, and then the NaOH, we're given the volume of 27.7 milliliters and the molarity of 0.444 molar. So it's like almost hopefully kind of hit you over the head that one of the things you're always going to have enough to get to moles. Then you're going to use the stoichiometry to get to the moles of the other thing that has the question mark. And then from there, it just kind of depends. So in this case, we'll have moles, we'll divide it by that volume and get molarity. So, okay, it always just kind of depends. So first step, setting it up. Heather, for getting moles from this. And then Chelsea, will have you citrate. Is that milliliters?
Yeah.
Cool, gotcha. It's easier with the stylus, isn't it? All right. Thank you, ma'am. Any questions? Drum roll. Very good. Okay, Andrew. So we're on our way then to moles of H2SO4 using the stoichiometry, piggybacking on the moles that Chelsea wrote down.
So we start with that and then moles from.
Let's start with that number of moles.
Is that what it was?
Mhm.
Okay.
Kelsey, you have a dividing thing right there. Calculator part. All right, thank you. Perfect. And we'll go pick on you, Jason. So then last step is to take these moles, and we were after volume this time. So now that we have moles of H2SO4,
Oh wait, I messed it up.
no, we're after molarity. We were given volume. What do you think it is, Jason? What are we after?
Wait, is this right?
Moles of H2SO4.
Yeah, I know. How do I delete?
Oh, you can do the hurricane backwards.
Okay.
Cool, thank you. I think this will clear it up. So we're after molarity. So we have the moles now, and the volume is given in the problem. Oops, wait. Turn green. Thank you.
No. We do that every
Yeah. I'm sorry, this one down here. So that was the volume. 25. But the problem is, or one more term, yeah. You got it. Any questions? Be courageous, write it down.
think.
I said be courageous, but not that courageous.
Do what? Oh, crap. Yeah.
Yeah, that is it.
Oh, I'm still on a race.
So 3 sig figs?
Mm-hmm.
Cool. Units are,
What did that just do?
oh, I don't know. He held it. If you hold it there too long, it like does like a lasso. It's kinda,
What is
I
that?
think you want to circle something and relocate it. All right? We're good? You're good? Okay. Okay, so like I said, there's all sorts of different variations on this. Okay. Now this is kind of a slightly different variation. Let's read it and kind of diagram it underneath there. So it's working with the one that we just did with, you came up with the concentration H2SO4 based upon 25.0 milliliters. And, sorry, the NaOH. See, I have to read it several times. Because I'm like, well, what does that number go with? Well, I have to read it more. So here it's after what is the concentration of the sodium sulfate? Do you see where actually we can just piggyback, and I think that's the way the notes are set up. Do you see where actually the first step we did, and I can't remember who did it, but you guys somebody used the volume and molarity to get to moles? So if we piggyback on that and now go to moles of Na2SO4 that must have been produced. The catch here is the volume. And we run into this when we're combining two solutions. Do you see the 25 milliliters and the 27.7 milliliters? That's like the final solution volume. So basically, whatever moles you get from stoichiometry, you have to divide by these two volumes added together. That's the catch. So let's kind of step through it. So can you, do you have the moles of the NaOH we got last time? Was that point? Point 123?
.000.
Did it have some zeros before it?
0123. Yeah, there's only one.
Okay. Moles NaOH over 1. Use stoichiometry to get the moles. And we'll have Matt, after you set it up, Matthew, divide it out.
And that was moles of Na2SO4.
That was moles of NaOH.
Put moles on the bottom now.
Moles of NaOH on the bottom and moles of Na2SO4 on the top. So then you have to look at what their stoichiometric coefficients are.
Right.
Yep. I'm liking it. Oops.
What did
Oh,
I
yeah,
do something
you're
wrong?
right, you're right. Too many inmates. So you got it calculated, Matthew? Cool.
Is that it?
That's it. That's the first step. I know. We're going to have you then take these moles and divide it by the volume. Actually, I think the next step I have you finding what the volume is. So it's an addition there. Keep it back there. Very good. Thank you, sir. So, as is the case oftentimes with titrations, after you mix those two aqueous solutions, what is your total volume? And we'll go over to Chelsea to use the moles on the previous slide and the volume here to get molarity of your cute little sodium sulfate running around. I'll buy that. I don't think I'll be too picky, but you might want to put milliliters next to those two volumes, but that's very good. Okay, down there at the
So I'm
bottom
just gonna
then.
take this divided by that.
You got it. But then dress it up, because then you need to get the volume in liters instead of milliliters. But you're right.
Okay.
And Andrew, we'll have you divide it out.
Oh. This one or
this volume goes down here.
Okay.
Very good. Dum, 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 dum. Let me think. I'm liking it. Any questions? So all sorts of different ways that those can go. Okay, so I do have screenshots of these, and I think we'll wait till, we're gonna go forge ahead into this part. We're gonna look at one more type of problem, and I will show you these screenshots, but, okay. So Wednesday, in a couple days, you guys are gonna be doing titrations. Titrations usually take 2 solutions, but actually only one of the things have to be a solution, and the other could be a powder, okay? But we use burettes to basically kind of just like be able to kind of fine tune the liquid that we admit to the thing that's being received. So this is a burette, okay, and here's the stopcock. This is all the way open, by the way. Many of us have like tried to fill our burettes and had this open, and it's like it all pours out. There are gradations on here, just like your graduated cylinder, so that you can tell how much you've dispensed by how it moves, okay, in the column. So that's a burette. So in a typical titration, we have what's called the titrant and the analyte. These are great terms to throw on that vocab section of the test that everybody loves, okay? So here's my burette, okay, and here's my stopcock. We usually, oftentimes, the reaction vessel is a cute little Erlenmeyer flask. These are nice because they have a large opening, but they have nice kind of closed sides, so it won't splash out. So, like the slide says, we usually have the titrant. It's one of the reactants in here. Okay, and down here we have the analyte. So just kind of think of the 2 reactants are separated. Okay, and the analyte's a fixed amount, and we drip titrant into the analyte. That's kind of what we have going on. So this should play. Play, darn it. I'm cool with that. Running in the background.
Here, a sodium hydroxide solution, whose concentration is accurately known, is being added to a burette before titrating an acid of unknown concentration. The volume of sodium hydroxide solution in the burette is estimated to 2 decimal places. The sodium hydroxide solution is added slowly to a solution of the unknown acid in a flask. The acid solution also contains an indicator, whose color will change to pink when the acid has been consumed. As the acid begins to be depleted, some color change is briefly visible. The equivalence point in the titration has been reached when the last drop of sodium hydroxide solution turns the indicator to a pink color that does not fade with time. The volume of sodium hydroxide solution in the burette at the end of the titration is estimated to 2 decimal places. Now we know the volume of sodium hydroxide solution used in the titration and can calculate the number of moles of acid that were in the flask.
Okay. So, in so much as kind of still images, so like I said, we have the analyte in here. What you'll be doing, what oftentimes we do if the analyte is a liquid, is we pipette the analyte in here. Never forget to add your indicator, otherwise you'll never see the color change. That's happened to me too.
So with the analyte and the indicator in here, in the video we saw that was acid. We go ahead and we adjust our stopcock to go ahead and drip sodium hydroxide in. And it talked about this pink point, and not all indicators and not all chemistries of titrations is pink what you're after, but it's really common. So here the indicator is phenolphthalein. Okay, so I added sound to these. Anyway. So not all reactions are going to make it be good for titrations. First off, you need to have the two reactants need to be soluble, usually in water. You need to know the stoichiometry of the reactants. You can't have to wait forever in order to reactants to proceed to form products. You can't have a bunch of side reactions, so it needs to go essentially to 100% completion. Okay. And I mentioned the phenolphthalein. It's just a very common, when you're mixing an acid with a base, okay, phenolphthalein works great for most acids and bases, or strong acid, strong base, I guess I should say. So don't forget to be able to, the end point, did you catch that? Because I mentioned the analyte is in usually the Erlenmeyer flask, and that's fixed. Okay, so what you're doing is dripping the other reactant until you use up all of the analyte. And the thing about the phenolphthalein is it turns pink when sodium hydroxide or base is in excess. So that's kind of how that works. So there are these two E points, equivalence point and end point, and they are very similar. I mentioned a minute ago that basically you're adding titrant until you use up all of your analyte. Okay, so there's the point at which you see it. Okay, I'll put a question mark here. There's the point at which you see it occur, and then there's the point at which it really occurs. Okay, if you were to be able to kind of look at all the little molecules of acid, in that case being consumed by base. So hopefully they're the same. Okay. So the phenolphthalein indicator that turns pink, you know, if you've used up all your acid, but you can also stick a couple of electrodes in your solution and look at its conductivity and know that you've reached an endpoint when its conductivity changes. All right, so let's do one. And we'll go ahead and kind of diagram underneath there the situation and what we're after. So here, somebody used a 50 ml pipette, and they transferred probably to an Erlenmeyer flask 50.00 milliliters of acetic acid. So 50.00 milliliters. I like kind of putting the information under the reactants because then I can see what I know most about. And it goes on and it says that this molarity is associated with sodium hydroxide. So I'm going to put 0.1150 molar under the NaOH. Then it says, all right, so if you read this, it goes ahead and tells you that the amount of sodium hydroxide you used, the video we watched, it actually, I couldn't catch it, but the starting volume in the burette was 0.48 milliliters. You never in your burette go full. You never go at 0.00. So we start a little bit under 0.00, so 0.48 milliliters where we start. After we dispense sodium hydroxide, the volume on the burette read 23.90. Do you see where we can, by subtraction, get this volume? Does that make sense? By subtraction. Are we good with that? So now it kind of gets back to what we did before. So we have the volume and the molarity. We can go to moles of this. Okay? And then we can go from moles of sodium hydroxide to moles of acetic acid using stoichiometry, the boring 1-to-1. Okay? And then we can take those moles and divide it by the volume there to get to the molarity. I'll just put a 3 there. So, here we go. Let's do that problem.
So the first thing, according to my builds, is, let's see, where were we? Oh, here, okay. Thanks for being honest.
I didn't want to be.
Here you go. So the first thing we're gonna do is come up with the volume of titrant. And we're gonna subtract the final burette reading, we're gonna subtract the, we're gonna take the final burette reading and from it subtract the initial burette reading.
Okay.
Hold on, notes here.
Yeah, I got him. So I'm pretty sure. Some titration. So, you want me to do it down here?
Mm-hmm.
Should I start with the NaOH?
So you're gonna start with that final burette reading.
Okay. Which is
But you're gonna do subtraction, so it's not a ratio here.
Oh, it's not?
So ratio comes next.
Okay. So subtract this from, what, 50?
The initial burette reading.
40?
Mhm.
40.
So Jason, do you subtract those numbers? Or, well, let's
You
let
want
you,
me
yeah, cool. I'll let Tyree do it. Oh, wait a minute, Jason did it last, we're on to Matthew, right?
Yeah.
Okay, okay. So the next step is we're gonna take that volume and use the molarity that was given to get to moles of NaOH. Okay. Ah, sneaky. Good job.
That would be
Heather, can you tap that out for us? Very good. Any questions for Matthew? I'm liking it. And we're going to use stoichiometry to get to moles of, thank you, moles of the acid, CH3COOH. Heck yeah. I like how you kept 4 significant figures now. Oh, actually, that's Heather, very good. Oh, actually, he's going to divide it out. Very good. Why don't you go ahead and write down that? I'm going to have you.
I was supposed to say it first.
Yeah. We're gonna let her
Oh, crap.
Excellent. See, I amended my slides for Doceri. So, take the moles, divide by the volume. I'll let that forget. Kelsey, divide that, if you would. It looks so easy when you're doing like it's a group. Yay. Any questions? Perfect. Okay. Well, I bet you guys were thinking, well, there's not an assignment slide till the very end. Well, so I'll do some screenshots of those four questions and now this question. This question's also due. So let's take a look at them. 550 will also be due Wednesday. All right. Let's see. Where did they go? For those of you, sick people, no. For those of you who like working chemistry problems, you'll like these too. So what I've done basically, there were 4 problems assigned earlier. This is the first of the 4 problems. Once you lift the information out, hopefully it kind of hits you over the head that you can use volume and molarity to get to moles, use stoichiometry to get to moles of this, and in this case you're going to use moles and molarity to get to volume. Okay? The next one? Let's see, how do I do this? Okay. 52, it's got 2 parts. It's got A and B. And so notice I've written down A. If you read A few times, and don't be like, oh my gosh, I have to read it too many times. Well, welcome to chemistry problems. Okay? So if you read A, you see that they give you the volume and molarity, the HCl. They're after grams. Now, grams in this case. I told you that not always with this sort of problem will the reactants both be solutions. But check this out. You're going to do what we've been doing in that you're going to use this volume and this molarity to get to moles. You're going to use stoichiometry to get to the moles of the calcium hydroxide. If you have moles of calcium hydroxide, can you use the molar mass to get to grams? You bet you can. So it's just different. And then actually B is very similar. Notice that the thing about B is the information about the HCl is given here. You know, you're given the volume of HCl solution, which you're given the density of the solution, and you're given the fact that it's only a certain percent HCl. So I've given those hints there for you. But bottom line, you can take this to get to the moles of HCl, use stoichiometry again to get the moles of calcium hydroxide, use calcium hydroxide's molar mass to get to the grams. So 61 looks like it's maybe a little bit easier, maybe not. Can you guys take the mass and get to moles of this? Okay, yeah, we didn't talk about it in part 9, but we talked about it earlier. Once you have the moles of the H2C2O4, you can use stoichiometry to get to the moles of the NaOH. Once you have moles of the NaOH, you have volume, you can get to the molarity. Okay, so just a different sort of twist. Now this is my favorite. Okay, I'll just give you a hint that basically my hint is that you start here. And I'm not going to kind of belabor it. Those other ones are more straightforward. I probably on a test would not give you this one. Okay. So let's take a look at that problem number 50. So the reason I threw 50 here is, doesn't this look like what we just did? Yeah, that's what I thought. I'm like, hey, we can do this. Okay. Given the volume and the molarity of the H2SO4, and given the titration volume required that was in your burette, 23.31 milliliters, we can get to moles from volume and molarity, stoichiometry to get to moles of NaOH, and we can use moles and volume to get to molarity of NaOH. So they're all just a little bit different. Okay, any questions? All right, very good. See you on Wednesday. This one? Or the one before it?
Yeah, I was thinking about it.
Okay. But this one really isn't that bad. But my hint, like I said, is to see how much excess HCl you have and then kind of backtrack. Okay? Fun and games till someone gets hurt.